So the particles you can see here can vibrate to and fro. They can keep on passing the vibrations from one particle to another and so on. But there won't be ever a case where this particle would jump over and move and change its position and get past the neighboring particle, right? At again the same temperature, right? So this is because of the tight packing and the strong intermolecular force of attraction. Now, but when the solids get heated, if I take again the example of solid here, which is ice, you can see the particles are again in very random motion. Although they are very close to each other, but they are vibrating to and fro, and they keep on passing this vibration from one particle to another. That is, in the vicinity, they keep on passing the vibrations from one particle to another. Let's now move on to neon, because the particles are again in singularity, therefore understanding this would be easier. Now, as we can again see, the particles are vibrating to and fro. Now, if I supply some heat to it, you can see that with increasing temperatures, as you can see, it is 37 Kelvin and so on, it keeps on increasing. The particles are now moving further away from each other. Now, the reason behind this is that when heat is getting transferred, when the energy in the form of thermal energy or heat energy is being transferred to the particles of matter, they start moving away from each other. That is, on passing heat, the interparticle force of attraction reduces. So when heat is supplied, when heat is increased, the interparticle force of attraction decreases, which eventually means that particles will move away from each other and the interparticle distance increases. Right? Now, it can also be seen in this activity, in this simulation in fact, where I take liquid, for example, and I start to heat it. On heating it, again the particles of liquid keep on moving farther away from each other. The same can be seen in case of gases. On heating, again the particles move far and far away from each other. That means they are in more and more random motion. With increase in temperature, as you can see, it is right now at 89 or 95 Kelvin, that the heat is increasing, the randomness in the contents of this vessel is also increasing. So this is what this portion says, that when solids are heated, their particles vibrate more vigorously, and a stage is reached when these vibrations become so vigorous that they start leaving their positions, and the interparticle force of attraction gets weakened and the solid gets converted into liquid state. So when I keep on heating this cube of ice, what happens is that the particles get heated and they start moving from one place to another. That means the energy becomes higher and the interparticle force of attraction therefore reduces, thereby converting the state of matter of ice from solid to liquid water, as you can see in this case. Right? Now, the temperature at which the melting of any solid substance takes place is called as a melting point. Now, melting point is that temperature at which any substance, any solid substance melts or converts into liquid state at atmospheric pressure. That means the pressure exerted by the atmosphere on us, which, as you have studied in force and pressure, is 180 M. That is 1 atmospheric pressure. So the temperature, the minimum temperature at which any solid substance converts its state into liquid or changes into liquid at atmospheric pressure is called as a melting point. So melting point of ice is 0 degrees Celsius or 273 Kelvin. Right? Now, you can see some examples of melting point. Ice, 0 degrees Celsius. Urea, a solid which again melts at 133 degrees Celsius. And iron nails melt at about 1538 degrees Celsius. That is 1538 degrees Celsius. Now, solids have a definite shape and volume. What about liquids and gases? Is a question asked by this girl in the book. Now, when I talk about liquids, As you can see here, liquids already have loosely packed molecules in them. So therefore, I can understand that when they are in random motion, they are moving from one place to another. That means the shape is not fixed, right? Let's take another example of it. So in case of liquids, I have a vessel. Let's change the colors to white. Yes, I have a vessel, and in this vessel I have filled some water, right? You took some water from a friend and filled it in a bottle. Let's take this as a bottle having 500 ml water. Now if I transfer the contents of this vessel into some other vessel, the volume will always remain the same. That means I will be able to transfer this 500 ml water from one bottle to another without any change in volume, right? If all the water gets transferred from vessel A to vessel B, there will be no change in volume. But what if this water from this vessel is spread on the ground? The volume will still remain the same, but when I look at the shape, water occupies the shape of the container. It takes the shape of the container and the shape keeps on getting changed. So the shape changes from one situation to another, but the volume remains same. That means the volume is constant. In every case, volume is constant, right? So it means in case of liquids, the volume is same, but the shape changes. This is for the case of liquids, right? Now coming on to gases, before I move to simulation again to make you understand this, coming on to gases from liquids only, if I have a container in which I have some liquid stored and I keep on heating this liquid, if I keep on supplying some heat to this liquid, there will be a time when all of this liquid will convert into gas, right? And we know that this process of conversion of any liquid to gaseous state is called as evaporation, right? Now evaporation can again occur with boiling as well. Now there's a difference between evaporation and boiling. Boiling will take place at exactly the boiling point of any given liquid. For example, water, it boils at 100 degrees Celsius. This is the boiling point of water, right? But evaporation can take place at any point around the boiling point. Why? Because evaporation occurs for the molecules which are on top. यानी कि evaporation जो होता है वो सिर्फ उन molecules के साथ होता है जो कि ऊपर की तरफ लाई करते हैं. Boiling तब होती है जब सारे के सारे molecules के अंदर evaporation होनी start हो जाए. That means जब सारे के सारे molecules चाहे ऊपर वाले हो चाहे अंदर जो present है वो molecules, so that is the molecules in the bulk, change the state of matter from liquid to gas. In case of evaporation, only the surface molecules convert into gas, vaporize. I'll just write only the surface molecules vaporize. In boiling, bulk and surface molecules both get vaporized. Both vaporize. Now, so when I keep on heating the liquid, what happens is, on heating liquids, as I showed you in the simulation, the heat energy transferred increases the energy or vibration of these particles and they move even more randomly. So there is more chaos in the system. They keep on moving more and more randomly, which makes them move away from each other. So the more the randomness, the greater is the distance between the particles. They start pushing away from each other. Randomness increases, the distance between the particles increases and the force of attraction reduces, which results in further increase in the interparticle distance, resulting in formation of liquid to resulting in the formation of gaseous state from the liquid state. Now, which this can be seen again from the simulation, which I'll show you in a second. Here is the liquid. I keep on increasing the temperature. You can see the particles have started showing the chaos and absolute madness in the system, where we can see that the particles are moving randomly from one place to another inside the system, inside this system of reaction where the reaction is taking place. And the more the randomness is, the greater would be the interparticle distance. Now they are moving far and far away from each other, and greater is the interparticle distance, the lesser would be the force of attraction, which would mean that the particles are no more in close affinity to each other, are not very closely associated with each other, not closely bound with each other, and therefore the randomness keeps on increasing. You can see जैसे जैसे टेम्परेचर बढ़ता जा रहा है, रैंडमनेस बढ़ती जा रही है. रैंडमनेस के बढ़ने से क्या हो रहा है, जो मेरा लिक्विड था वो गैशियस स्टेट में कन्वर्ट हो गया है. नाउ यू वोंट फाइंड any mention of liquid here. There is no mention of liquid. I selected liquid. Now it automatically got deselected. Why? Because it is not a liquid anymore. It has converted into its gaseous state at this temperature, which is about 270, 286 Kelvin, whatever, depending on what matter it is, that is neon. So it has already converted into its gaseous state. Same can be observed with water. In its liquid state, this is what water is. If I keep on increasing the temperature and just convert the units into Celsius, it is at 46 degrees Celsius right now. I keep on heating it. It has reached to 100, about 150 degrees Celsius. And now you can see how the particles are in random motion, how they are moving farther and farther away from each other. This is because the interparticle force of attraction has reduced, the interparticle distance has increased, and the particles have now, of course, vaporized at this temperature at 500 degrees Celsius. There won't be any water in liquid state. It has, of course, vaporized. And vaporization would mean it has converted into gaseous state. And now in some particles, as you can see, they're absolutely in completely random motion, absolute chaos, with the energy levels are too high. Now, coming back to the contents of the chapter, this is what is being explained here. They're saying that they've placed water in 3 containers. In container A, 200 ml, container B, 200 ml, container C, 200 ml. The volume remains the same. सब में volume 200 ml है, लेकिन shape acquire करता है liquid उस container के जिसमें उसको store किया जाता है. So it has acquired the shape of the container in which it has been stored, but the volume remains the same. So liquids have definite volume, but not definite shape. They have an indefinite shape. Now, when I compare the particle distance between solids and liquids, I can very easily say that I can't move my hand through the solid particles because through any solid state, because the particles are very closely packed. I cannot move my hand through a wooden table. Why? Because the particles are so closely packed, so tightly packed, that there is no space, there is no interparticle space in between the molecules of that solid. In case of liquid, since there is an interparticle space, therefore I can somewhat easily move my hand through liquids, although not as easily as compared to gases. So if you try to walk in water, you will find that there is some resistance there. You are not freely able to move in underwater. And of course, when I keep on increasing the density of any liquid, the movement becomes more and more difficult. So compared to solids, yes, the movement, or of course, I can cut through any liquid very easily with my hand. Same cannot be done in case of solids. So therefore, it is primarily because of the interparticle spacing, which is quite loose in case of liquids.